Alright, time for another DraftPhysics.com, debatephysics.com, also video presentation. So another math and science video. Guy's name is Jason. Teaches online. I don't know if he was ever a teacher. He did work at NASA for a while. Doing what? I don't exactly know. But anyway, so he makes physics videos. Okay. And I'd argue that, they're, as conventional science goes, pretty averagey. And so now he's got a high-speed camera, so his videos have gotten a little more interesting. It's not just the math. You actually get to see something. But you'd almost argue that, the more they show, the more it doesn't fit what they argue, is the physics. Because their math doesn't model reality. It just, circularly completes itself, but it doesn't applicably connect to reality. So they'll say something like Newton's laws are relevant, and then in simple examples like this one, where he's talking about pressure, and so it's a can of air, compressed air, which is compressed hydrocarbon of some kind, butane or something else that's actually coming out of the can, but regardless. And he's talking about expansion and pressurization as they increase temperature, but they don't really do that. They only do that when they're in an extreme state of expansion or contraction. It's not exactly the contraction and expansion itself that's causing the temperature. But anyway, if you did it slowly, then you wouldn't have a temperature increase or decrease. It's only because you're doing it quickly that it changes temperature. But anyway, the real point I want to make, there's a lot of real points. You can just see from this nozzle. Okay, so this is the nozzle on the compressed air. He's got it upside down, so the fluid's coming out, not the compressed air. Which really isn't the same thing. But anyway, and it's a perfect example of how kinetic energy fails, because there's no equal and opposite reaction. So as the propellant is shot out at a high velocity, the can won't receive the equal and opposite kinetic energy reaction. So it's only a momentum equal and opposite reaction, not a kinetic energy equal and opposite reaction. So in fact, you have a whole bunch of kinetic energy flying one way, and you don't have the same amount flying the other way by a huge differential, like thousands to one. So you could say like there was 2,000 joules of energy shooting out one way, and there's only two that actually get the can's equal and opposite reaction is only two. So clearly Newton didn't believe in kinetic energy, because if he did, he wouldn't have written a third law, because it's violated by anything that shoots things that are lighter than it is or heavier than it is, because it'll never be conserved in those circumstances. So unless you're propelling something of your equal mass, you won't conserve kinetic energy. So that would be the more interesting subject. Lots of things you could do with this high-speed camera that they don't do, unfortunately. So we'll get through some of this, but I guess we'll talk a little bit about pressure. So I'll play a little bit of this.
I want to do a really cool little demo. You can get these cans of air.
So he's talking about the cans of air while he's showing a completely different demo where he compresses air quickly. All right, and creates enough heat to burn some cotton in the cylinder. But he could create the same air pressure slowly, and he wouldn't have burned it. It's not so much about the pressure as it is how you acquire the pressure. All right, so we'll just jump a little bit ahead, play a little bit of
the
this.
slow motion video. So I'd like to do that. First, let's take a look at what it looks like, and then I'll show you how the temperature goes down, and then we'll talk about exactly why it happens.
So his exact why is not exactly why. So would be the argument, because they don't have any of the physics right. Look, it's a push-averse, okay? And stuff has to be pushed by something. It can't be pushed by nothing. Yeah, but anyway. So there's a lot of this, okay?
And when the stream starts to
but
cut
not
off, look
really.
at the way that
So, you shoot it out, the liquid this way, and he talks about the liquid curling around the surface, and we know it adheres for a reason, but it's just basically you're moving the air, you're pushing the air out, creating a vacuum, causing the air to move in the opposite direction. So all of that's understandable. It's just common turbulence, blah, blah, blah. And so there's a lot
it's just
of
very
this.
hard to keep something this.
Yes, he talks about how difficult it is to film and blah, blah, blah.
It's kind of using the surface tension. The surface tension is pulling it around the lip of that green nozzle.
Yes, it is. Anyway, and continuing.
Kind of a diffuse cloud, and then finally it cuts off, and you can see.
Yeah, it's very interesting, sort of, maybe. Anyway, so let's see what else he says here.
That like I was able to do with my zoom lens, with my macro lens, you could.
So he keeps, a lot of details about the fact that it's hard to do, blah, blah, blah. And then he shows how the temperature changes as you release the gas. The can gets colder. And what's getting colder, for obvious reason, you're expelling, a bunch of stuff that was in the can, banging against the can's walls, and now it's not in the can anymore, banging against the walls.
We're starting off at 77.4 here.
All right, so interesting, but not that interesting.
Why does it decrease the temperature of anything? That's what we want to talk about next. I think to motivate the discussion, what I want to do is go in reverse first. We're learning that expanding a gas, allowing it to get bigger, is actually cooling off.
So allowing it to get bigger is cooling off, and it's really not. It's just that you've obviously, if you have certain stuff in it, if you had a bunch of stuff moving in a container and then you let some of the stuff go, then obviously the container can't be as hot as it was because there's not as much stuff hitting it. I suppose it's the more detailed argument will be the one I'll make. Might as well make it now. So I'll do a little drawing. All right. So the problem with conventional physics is, yes, they think everything is a mathematical formula, and that's the physics. The physical world is these reductionist, abstract formulas. They aren't supposed to be abstracts. They're supposed to be almost axiomatic, but they're not precise enough to be axiomatic. They're just generalities. And the fact is a lot of these formulations are just plain wrong. Like 1/2 mv squared, it's just wrong. So they have a bunch of wrong, formalizations of the functions, and they're like radically wrong in this case, where obviously when a can is expelling a gas, there is no equal and opposite reaction to the kinetic energy. It's obviously that idea that this 1/2 mv squared function of energy doesn't really exist, and all that really works is momentum. Anyway, so I'm arguing that universe is a push-averse. Okay, so there's electrons and protons, and I won't get into the distinction between them, but the idea you can understand is I'm arguing there's a force in the universe that moves the speed of light. The stuff that makes photons, makes gravity, makes magnetism as effects, those are all being controlled, and charge makes electrons and protons move. And the fact is it's this discrete force moving the speed of light. And the simple truth is that you can understand that just if I had a universe, that was just full of these little pieces of force, little tiny bits, and they would hit, in a kind of randomized way, that there'd be a certain amount of motion. Something would move around a certain amount. Now, if there was nothing else in the universe, that is nothing to create changes in the density of that force, it would just have this little bit of motion. That's all it would do, is this little bit of jiggling. And the idea is it's because we live in a universe full of electrons and protons that the force ends up being put into clumpiness, where there's a whole bunch and then there's nothing and then there's a bunch and then there's nothing, kind of a thing. So things start getting moved around. And the idea would be is that every time a little piece of force hits an electron, let's say the force was 10% of the mass. And so you would argue that now you have 11 units of mass. All right, and you've got 1 unit of force. So, it's 1/11th. Okay. And you could understand that with each additional bit of force, okay, that each bit is going to dilute how fast it's going. So it'll go faster and faster, but it can only go a percentage of the maximum speed of the force. So the first force bit, say it was 10% of the speed of light. Then the next one is 10% of the 90% that's left over. So it's only taking 1/9, and then the next one will take only 1/8. And obviously the percentage will get infinitely, you'll get bigger and bigger decimal points as you get towards the higher and higher amounts. You'll make less and less of a difference. But the key point is that the speed of light force, okay, is affected more, okay, when it's just one bit of force going back and like one hits it this way, one hits it this way, one hits it this way. It has to stop in between those. So if it moves, it has to stop and then go in the opposite direction. Then it has to stop and go. And so it never goes any faster when it's in its small amount of jiggle. It can never go any faster than 1/10 the speed of light. But if it can get hit by a clump of force like this comes at it, then it can go much faster, okay, than 1/10 of the speed of light, and it might go 80% or 90% of the speed of light. And you can understand that that means that all of these bits of force are almost going their actual universe speed. They haven't lost any speed. So if there's one bit of force, the bit of force has lost 90% of its energy, so to speak. It was going, 100, and now it's only going 10. If we put it in miles per hour. So its maximum speed is 100 miles an hour. It's only going 10 miles an hour when it's pushing an electron. But if there's 2 of them pushing, then it's going 19. And if there's 3 pushing, then it's going 28 or whatever. So it's going faster and faster and getting closer and closer to being unaffected, in the sense that it's going to get where it was going because it's still almost going its original speed. So if you can hit an electron with like a gamma ray or something with a high density of force, then it will move almost without taking any energy out of the force, because the force will arrive at a location in the sense that it'll be carried by an electron that's still going almost the speed of light, and therefore you've conserved the energy of the force because it's going to get where it was going in the same amount of time, where if it's only going 10%, it's lost a lot of its, where it would have been is much different than where it's going to be, because it's only going 10% of the speed it would have been going. All right, now that sounds complicated, but I'm just saying it's not that complicated, right? I mean, it's easy to understand that the more things that are pushing something, the faster it's going, and the faster it's going, the faster each of the things pushing it have to be going. So if there's 2 people pushing and it's going 20 miles an hour, both of those people have to be going 20 miles an hour. And if there's 3 pushing and it's going 30 miles an hour, you can understand the 3 people are all going 30 miles an hour to still be in contact and still be pushing and still be relevant. All right, so there's no such thing as like this idea that something gets hit by a force and it moves magically. It has to be pushed constantly. So no piece of matter moves because it collected just motion. It's collected an actual element in the universe, okay, the force, the pushing force. So anyway, that's one aspect of this. So you can understand that an electron is created more cold in the universe the slower it's jiggling, and the faster it's moving, whether it's even just in a linear direction, the faster it's moving, the less cold, that is, the less it's absorbed heat out of the universe. So in a sense, it's hotter the faster it's going, and it's colder, okay, the slower it's going. It's absorbed more energy out of the universe. I don't know how, it's the only way to say it. All right, and so I'll think about the other part of that I want to get to. I think the bottom line is you understand that when you pressurize something, what are you doing? You're taking stuff that is separated by a distance, and it's created a thermal equality with whatever you have put it in. So whatever container it is, it's created a thermal equality in that it's hitting the surface, and that surface is radiating the energy, okay, of its temperature. So if it's hitting, and it's really just about how many times it hits and with how much velocity it hits, right? So that's the whole catch to it. And a simple argument is if you make a hole in that, you can understand that that piece of energy now leaves the box, and it won't be reflected back into the box. So whatever the temperature is inside has to get colder, all right, because you've let something out that now isn't in the box anymore. That piece of temperature, okay, that thing that was hitting the surface isn't going to be hitting the surface anymore because it left. So it's not in the system anymore. It's not going to be hitting the other particles, if you understood that too. The matter is obviously capable of reflecting energy back and forth to each other. And so you've basically just taken a piece of it has equalized its temperature, but it has to get colder than whatever it's equalized at. So it doesn't matter whether I have it at 100 degrees or I have it at 50 degrees or I have it at minus 200 degrees. The fact is that if I let some of it out, I've got to make it colder because I've no longer have that in the container to create the equilibrium with the rest of the universe. And so the universe will compensate, and it will reach equilibrium again over time. So it's really just about how quickly I do that. So if I do it very slowly, you're not going to notice any temperature change, because if I only let one atom leave per day, it's going to be a tiny difference in the overall temperature, so you're not going to notice anything. But if I let a billion of them out, then I'm obviously going to change the temperature rather radically, and it requires a billion interactions to re-equalize the temperature, to equalize the amount of bouncing going on in the inside with the amount of bouncing going on the outside, and that's what has to be equal. So essentially the pressure of the little bits, if I have stuff wobbling over here and that wobble throws stuff at some other thing over here, then they're going to communicate with each other in that sense. They're going to share that information. Now, when it's sharing it as force, even though it's moving the speed of light, the force itself isn't very dense in the sense that it's not like it can't, per unit of stuff, it can't carry as much energy as, say, a moving electron. So it takes time for you to transfer energy by just radiating it as infrared radiation, for example. So that's the slow way, and the quicker way is to have a whole bunch of atoms that'll get hit, and they'll absorb the energy and move out, they'll absorb the temperature more rapidly because they have electrons that can absorb temperature. They can absorb electrons and slow them down. Things that were going the speed of light, it can turn into things going half the speed of light. All right. Might be good enough. All right. I'm going to mix a couple of subjects just because I thought of it, with the high-speed camera, it would be interesting if they would do the Newton's cradle, where they could put an impediment, just a piece of metal between, the same hardness, and see if you can transfer, the energy through, what the profile has to be for you to maintain the transmission of the energy. So does this have to be the same mass as this, or is it really just about this distance here for transmitting, say, the energy of this swinging down and hitting? If this is the same thickness, would that pretty much just transfer the energy because they are making contact with each other? So this should be, I should have this drawn closer. They're making contact, and just kind of show how the force is transmitted as just motion inside of the object when they are in contact with each other, and and how much separation would obviously mean that this object would have to be able to move, and that would consume momentum. And the idea is to see if you could do it without consuming any momentum. And you could see a little bit of that in Steve Mold's video, where when he tried to make the lever, he ended up making a piece of metal that really didn't move. The one ball hits here and the ball pops off here, and the lever itself doesn't visibly move. So, it's just a curiosity. All right, so that sort of relates to understanding, that what's happening with temperature transfers is that you have a temperature on one side and you have a temperature on the other side, and whatever side is hotter, the simple idea is that it has more velocity. That is, the little bits are being hit by a higher frequency of force in clumps. So there's force and then no force and then force and no force, and that means it gets to a higher velocity. And so when it hits the wall, it's at a higher velocity. It pushes on the wall further. Say this was the hot side, and so this is substance, this whatever this is made out of, it moves faster this way than it moves back. So it moves back slowly and it moves out quickly. And so that's how the temperatures equalize, is that all of the fast motion is getting absorbed to restore this side to the same. If you thought of it as a pendulum, you could sort of think about a pendulum oscillating. And if the pendulum is only oscillating this little distance, it can only be oscillating at a very slow velocity. And if it's oscillating at a high distance, then it's oscillating at a very high velocity. And so that's all you're really doing, is you're saying there's a velocity on each side, and if this side has the higher velocity, then it's going to start making this pendulum swing, these atoms vibrate at a faster rate, because they'll get clumpier. And it really just has to do with the clumpiness, how separated the force, the average force is, and how concentrated it is. So if it has elements of higher density, then it's going to end up being hotter than if it has an average density where there's no where they could have the same density. It's just that one of them, the density is clumpier. So the clumpier the force, the higher the temperature. And that sort of goes with the idea that at higher temperatures you create higher frequencies of radiation, and the limit being the the ultraviolet catastrophe type thing, where it's very difficult to create enough velocity, to create the ultraviolet and obviously X-rays and gamma rays. You need a special circumstance to be able to create velocities that high. Alright, so that's probably enough of that. So we'll play some more video. Alright, so this is the part where he's talking about making heat. So the idea is he's going to pressurize the cylinder, but he's going to pressurize it quickly. And because he's doing it quickly. That is, there's no way for the thermal change, in the sense that he's got a certain amount of stuff in a vessel, and he's going to compress how much space it has. Obviously, it's going to hit the walls more. So it's sort of like arguing about the double slit experiment or some other, where, you know, the obvious point you could make is, okay, the wider the slit is, the higher percentage of the light goes straight through, and the narrower it is, the higher percentage of the photons that'll be near the surface and create fringes. So there's not like more fringes, it's just that there's less light going straight through. You know, sort of the obvious kind of argument. And so in this case, he's only creating heat because he's contracting how much space the same amount of stuff has, and it's going to hit the surfaces a lot more often, so it's going to transfer, okay, its differential to the surface much quicker.
Experiment a while back where we actually had a cylinder and you can use your hand.
So it can't get rid of the heat quickly enough. So that's why the temperature builds up, is because you've confined the amount of space, and but you haven't increased the amount of, you know, it's hitting the surface more often, but it's not hitting it. There isn't enough surface to dissipate all of the heat you're creating. Okay, so you're making lots of more contacts with the surface, and you have it in, and it just doesn't have enough time to dissipate the pushing out part.
And to slam down and actually convert some of the energy of the motion of your hand into raising the kinetic energy of the gas in the cylinder.
So if you just compress it, it won't work, you know, slowly, because then it has time to get rid of the heat. But if you do it quickly, then there's no time to get rid of the fact that you've got the same amount of motion in a much smaller space.
Even to the point where you can ignite a small piece of cotton in the bottom. That's what I have in the bottom there, is a little piece of cotton. And the reason the temperature goes up under compression is because the molecules are bouncing off my, if you pretend my hand is the cylinder face.
So he's saying he's making them go faster, and he's really not. You know, you can't, so they're going the speed of light, you know, the force. And even the electrons and protons and atoms, you're going to move them, what, 50 miles an hour? I mean, 50 miles an hour isn't going to make them, you know, have all of the capacity to make all this heat. So it's really not about the fact that you're pushing them and giving them extra motion. So he's going to argue that essentially as he pushes the plunger, the stuff that's hitting the plunger is reflecting faster, but it's such a tiny amount of faster. I mean, you're talking about stuff going, you know, hundreds of thousands, if not, you know, hundreds of thousands of miles an hour anyway, whatever, if not 3 million. And, you know, there's just no way that 50 miles an hour could make any real significant difference. So it's not about the fact that you're giving them a little bit of extra momentum. It's about the fact that you've dramatically reduced the amount of surface that they're confined in, so they're reflecting a lot more often in the same space. So whatever's in that space, they're hitting a lot more often because they have less opportunity to do anything other than hit, because you've made the space smaller and smaller and smaller. So they have to hit stuff more often.
It's bouncing off all the time, going in the opposite direction, trillions of times a second. But if I start compressing and ramming it really, really, really fast and quickly and rapidly, then...
So let's understand, his rapidly is 34 miles an hour. I mean, it's not even close to fast enough to make a difference.
As a molecule comes in, I'm going to give it more velocity as it bounces off, just like a tennis racket or a ping pong racket hitting a ping pong. As the ball comes in, if you hit it, it's going to bounce off with more velocity.
So I'm just saying it's a bad argument physics-wise, because it's, like I said, the little particles are moving a lot faster than that 30 miles an hour, and you're really not going to be changing them enough to create that dramatic increase in temperature, you know, hundreds of degrees in temperature. And why, you have this very high temperature changes as you went from, 1,000 milliliters to 10 milliliters of space for them to occupy. And now they're going to hit that surface and hit each other a lot more often.
And I'm doing that to trillions and trillions of gas molecules when you compress a cylinder like that. And so by compressing the cylinder, then it increases the temperature because you're increasing the velocity of the gas molecules. Eventually, you get it hot enough to combust the cotton that's in there. But if you noticed really carefully, if you look at that video, as I reach the end of the travel of the cylinder and it kind of bounces off so that the cylinder is beginning the expansion phase.
Right. Well, it won't really do the expansion phase. First, you have to have a compressible gas, of course. And, the real question is if you actually ignite something, then you're going to get, a blowback effect of higher pressure. So that just has to do with the fact that you have oxygen available and you can burn the material. And so now you're increasing the pressure inside because you've created all that extra heat.
And then the pressure of the gas at the bottom is pushing on the cylinder and causing the expansion. So whereas I'm putting energy into the gas with compression on the downstroke, as it bounces.
So you're not really putting energy in. You're you're compressing it quickly. So again, the difference between the heat problem and the pressure itself and then igniting something are all three different ways of looking at this. But if you're just compressing air, you're only going to get so much blowback in terms of the extra pressure you created. I mean, you're only increasing the pressure from, say, whatever, atmospheric pressure to 100 psi. And then if you ignite something, then you might go to 500 or 700 psi.
Off, the gas is doing work on my cylinder, my hand in this case, and the internal energy has to come from somewhere. So the temperature of the gas is going down as the expansion happens on the other.
So any expansion causes temperature to go down just for the same reason, because you've created this opportunity for things not to hit surfaces and not to exchange temperature, so it can't exchange its temperature.
Side. And that's why the fire goes out right away as soon as I kind of like begin the expansion of it. And the reason that happens is because the temperature of the gas is going down. Same thing I'm talking about here.
I mean, anytime the surface, you're going to say, if the surface yields, then it absorbs the energy. And if it relaxes slowly, so again, if it's pushing out quickly and it's pulling back in slowly, it's going to be a net increase. It's pushing energy out, and there's a net decrease in how much energy goes in.
The temperature of this thing goes down when the gas is expanding. The temperature of the gas in that cylinder is going down when the gas is expanding. And I'm going to talk a lot more in just a second, but in a nutshell, the reason why is that when I compress a gas, I'm literally forcing the work of my hand to go into increasing the kinetic energy of the gas molecule.
So again, they don't have any kinetic energy, and that's proven when you release the gas, you don't get an equal and opposite reaction. So it's obviously there is no kinetic energy, but you can't transfer it to the can. So again, they keep saying this stuff exists, but there's no evidence that it exists. So it fails with a lever, and it fails pulleys, and it fails ballistic pendulums, and it fails rocket thrust. It shows there's no evidence that kinetic energy ever does work. There's no evidence, obviously, that 20 times, 25 times the fuel to spin something 5 times as fast, or that something spinning 5 times as fast can do 25 times the work. No evidence whatsoever.
I'm doing work on the gas.
And so there's no work on the gas kind of argument beyond the fact that, yes, if you do it quickly, yeah, you'll create heat. And obviously, yes, it takes work to change the pressure inside of something, to force the molecules to be in a smaller container. Yeah.
And from thermodynamics, when you do work on a gas, the energy has to go somewhere, and it goes into the internal energy of the molecules, which means they get moving faster.
So the fact is they won't stay that way, and they'll still be under pressure. So the fact is the temperature will equalize. So even you could pressurize the air, it'll get hot, and then it'll equalize with its environment, and it's still under pressure, but it's not going to be any hotter. So you have to understand that that pressure is being created by what you're doing to the molecular bonds between the atoms, and the fact is the repulsion between the electrons. So that's sort of like just stretching a rubber band or something. It's more of a chemistry argument in some respects, because it's about the bonds between the atoms and how much they repel each other or how well they attract. And so obviously in this case, air molecules don't like air molecules. If they did, the air wouldn't, especially at temperature. You have to take all the temperature out. You have to take all the radiation, the infrared radiation out, or they're not going to be in stable positions.
And we perceive that as higher temperature and higher pressure also, right? But whenever the gas expands, then what's going
So again, it doesn't stay at a high temperature. So it's just wrong to say that somehow temperature will release the pressure, or somehow the pressure is temperature, because it's not really.
going on is the internal energy that was in the gas begins to do work on the piston. So it's reverse. At first, the piston does work on the gas, compressing it, making it hotter. But then it turns around and the gas begins to do work on the piston. And that energy also has to come from somewhere, and it comes from the internal energy of the gas.
So again, internal energy is just saying almost nothing. It comes from the atomic relation, the charge relationship between the nucleuses, the electrons of the atoms, and how well they interact with each other. And all you're really saying is the fact is they only connect in certain arrangements, and they can only be in certain proximities to each other, and especially at temperature. So the more force that's coming in, the more infrared radiation that's wobbling them at a higher velocity, the less likely it is they can get in a stable position next to each other.
Which means in order to expand the piston, then it has to come from somewhere. It comes from the internal energy of the gas molecules. That's conservation of energy, otherwise known as the laws of thermodynamics.
So, and again, it's just sort of bullshit to talk about the laws of thermodynamics when they think that there's some sort of thing called entropy happening, when when it's kind of obvious that gravity is the exact opposite of entropy.
Right? Laws of thermodynamics, it sounds so complicated, but it's basically a law of conservation of energy. We talk about work, we talk about heat, which is thermal motion of molecules, and we talk about energy. And in this case,
so it's it's just more the point is to see, this is where, yeah, these are nice little general statements, but they really don't get to the fact that it's a little bit different to talk about the energy between electrons and protons, and then talk about, well, I'm injecting infrared radiation that's creating heat, because one is the force you're adding, and one of them is just the nature of their condition, being electrons and protons.
piston does work on the gas, raising its temperature. It goes into the internal energy of between the gas molecules and their motion, and their rotations also. They're rotating as well.
So that's the who cares part. Yeah, obviously there is some rotation, there is some extra angular momentum, but electrons aren't spinning.
Does work on the gas, raising its temp. Then as it expands, the gas does work on the piston, and that piston is bouncing up because of the internal energy being extracted.
So again, it's no more different than any other elastic kind of storage device. So it's not any different than a spring or a rubber band. The air molecules it's because of charge. It's the charge between them and the fact that it's incompatible, and that these molecules won't combine and become smaller things. They'll just, and you're just pushing electrons into electrons, and it's the electrons into electrons that are saying, I'm not going to stay that way. So as soon as you give them the liberty to free themselves from their close confinement, they will spread out.
Distracted from the motion, the internal motion there. And so something has to give. It has to come from somewhere. So it comes from the internal energy and the slowing down of the gas molecules. If you want to think...
So slowing down, I don't know what that means. It has to be because you've sped them up, but you can't speed them up. That's the whole point. Because then they'd stay hot.
Think about it at a microscopic level, then we can draw the following picture. If this is the piston...
So he didn't draw this very well, and it's not very interesting, so we won't bother. I mean, I can just advance it a little. So he's basically saying, look, when he pushes here, he gave the atom more energy, and that's not why it gets hotter. It gets hotter because you've taken the energy that's in there and given it a very small area to fly in. So the average time it takes to hit a surface is now increased. So the surface is pushing out more. Pushing out fast, pulling in slow. Pushing out fast, pulling in slow. So it's sending the radiation out. All right, and then he draws the second one. This is the compressed cylinder. It's not very well. Should have drawn it this way and then showed it expanding. And so now he's saying, see, when I'm pulling it out, then the things bounce off and they lose energy. And they're losing energy because you've increased all this surface area. It's not this little tiny plunger that's, the key surface. It's all this extra surface they're now hitting. Okay, so they have the same amount of energy pushing on a huge amount of surface now. So they're pushing out a lot less per inch because there's a lot less per inch. So it's just about how much pressure you're hitting the surfaces with. And now if you expand the surface, there's less pressure hitting the surface at any one micrometer of surface is getting hit by less stuff per second.
Comes off with a smaller velocity than it had to be.
So it's just wrong to say it's about how quickly it's bouncing off this. It's obviously, see, if you would have drawn it right, this would have been a tiny amount of surface here, and you could make the argument, obviously if I expand the surface to this giant space, that surface has to get a lot colder. It's absorbing energy a lot more than having a small amount of transmission surface. All right, it's probably enough of that. Well, we'll play the end.
Begin with. That is why gases cool when they expand.
So it's not really right. Okay, so what he's saying is really wrong. The plunger has nothing to do with creating the heat. And the speed issue is just about the fact that, if you compress it really slowly, you won't notice the temperature change because it will acquire equilibrium.
Even when there's no cylinder. I'll talk about the no cylinder part in just a second. But with a cylinder, it's easy to understand. If you compress it, then the velocity of the cylinder goes into speeding up the molecules of the gas, which makes a higher temperature.
So it's just wrong. I'm saying that's just wrong. It's just about surface area, and you're reducing the surface area. You reduce it quickly. It takes time for it to re-achieve its equilibrium.
Out, it is still doing work on the environment. Here, the environment is...
So he's talking about the work done by the environment when he squirts so all of this kinetic energy flies out one end. The can recoil is, 1,000 times less energy. Obviously not obeying Newton's third law. Obviously, kinetic energy won't be doing any real work.
The cylinder, and it's doing work on the environment by moving the cylinder. What is this doing work on? It's doing work on the atmosphere. When it comes out of the chamber, it's pushing against the atmosphere. Right? We don't think about...
it's just atoms moving, and obviously they're going to hit the other atoms that aren't moving. It's going to move them, so yeah.
Atmospheric pressure, because it's always squishing us all the time. But there's 14 pounds of force for every square inch all over your body. That adds up to a lot of pressure. And so when the gas exits the nozzle, it is pushing against the atmosphere. You can think of the atmosphere as being...
So again, and it's only going to be doing that if it's more than 14 pounds per square inch, which obviously it has to be able to be expelled from the can.
A gigantic cylinder, but not a cylinder made of metal or glass, just a wall of gas that's pushing on it with a pressure. But yet this jet of air, as we saw from the video there, when I turned it upside down, you could see it more readily.
Yeah, it's not air, it's fluid. It's okay that you're ejecting, so it's really not the same thing, but whatever. I mean, obviously it's, again, a completely different equal and opposite reaction, right? So you have a higher density of material going much slower, and when he's just ejecting the air, it's going to be going faster than the fluid would be going. But it's less dense.
Like that, It's pushing against the atmosphere, right? And it's pushing the air.
So the important thing, though, is from the can's perspective, it doesn't matter whether there's an atmosphere or not, because all it's doing is ejecting material going in one direction, and it still has the other direction. So it was at equilibrium. You let a bunch of stuff out that was going this way. Now there's not an equilibrium. Now there's more stuff moving this way than it's moving that way, so the equilibrium has been broken.
Air out of the way, so it has to be doing work on the atmosphere. Where does the work come from? It has to come from the internal energy of...
I mean, if I just drew I just draw two lines, you can just understand. So this is two surfaces. So I can't change the equality. No matter what shape I make this, it's always the same, amount of stuff hitting a side, a surface, a direction. And what you're basically just saying, well, what if I put a hole in this? I can't make a hole easily, unfortunately. So I put a hole in it. I'm removing this hunk of surface. So obviously now there's stuff still hitting all of this surface, and there's only stuff hitting this and this. So you can understand I basically annihilated a piece of the surface. So if these two things were connected, you can understand that there's more stuff pushing this way than there is stuff pushing this way on the actual object. Could have done that better. Anyway, so and it's that simple. So even if I have a hose and I twist it all over the place, it doesn't matter, because all you're really saying is all of that is also being bounced off the walls, and the bottom line is, which direction did it leave? And whatever direction it leaves in, it means that way didn't hit a surface, and all the other ways did hit a surface. So it was at an equilibrium. I mean, it was we shared the same frame. We're moving through the same universe with the same amount of arrows, collectively, and then it gave away stuff going this way. So it has to go that way, because it gave away stuff going that way.
The storage of the energy and the motion of the molecules, i.e. its temperature. So instead of it bouncing off of a solid wall and doing this, these molecules are bouncing microscopically and encountering resistance to the air that's outside.
So that's just wrong. It's not the external air pressure is, a nuisance, you could argue. Look, I mean, there's this idea of finding zero pressure. Would mean that you're not going to stall the velocity at all. But the fact is, it leaves the can, at the velocity and has to meet the air pressure at some point. And obviously, when the first few molecules go out, they push all the air out of the way and are essentially creating a vacuum behind them. So the ones that follow aren't really pushing air anymore, and you're just losing them to the environment. You're just giving them away. Thrust doesn't need a surface to push on in most cases. I think in all cases. All the pushing thing could do is cause reflections, that would, bounce off and come back and hit you in and to force you to go again, and then it bounces off and hits you again. So I mean, it's of some use in the sense that it causes reflections, and then they get hit by the energy twice. I mean, not only did you give this away, but you got hit with something going this way, so you got a little extra.
And they're pushing the air out of the way. So the speed has to come from somewhere. And so it comes from the slowing down of the internal energy. And then that's conducted back through the whole thing inside of here, because it's expanding as it comes on out through the whole.
So all of that is kind of a mushy, loose, or hand wavy, as they call it. That was sort of hand wavy.
Whole thing there. Right, so this has applications in refrigeration, I'm going to talk about in just a second. It has applications in rocket.
So that's an interesting subject, but and again, I think he missed a key point. So we'll get to that.
Engines, you have a big expansion of gases in rocket engines.
So, but he won't be talking about the fact that kinetic energy completely fails to move the rocket, and the momentum completely succeeds, proving that momentum does work. Kinetic energy doesn't do work.
Expansions and lots of machinery where gases are doing expansion and rotating machinery. This is what thermodynamics is all about. When we
so not really. Thermodynamics is about completing the system in sense of understanding that it's all just big things moving and very, very tiny things moving, and it's about things moving in all one direction or things moving in all directions, and that's what it's really about in terms of thermodynamics. This is really hard to do anything with, okay, in terms of, unless you put it inside a pipe bomb or something, so in most cases heat dissipating energy in all directions isn't very useful, but dissipating it all in one direction like a laser beam is useful.
Compress gases, they get hotter, and the temperature goes up, I should say. And when we allow the gas to do work on the environment, or work on a piston, or work on some other machine, then its temperature is going down, because that work has to come from somewhere.
So just think how much how much energy you get from the ocean if you could collect all of the rays of pressure, that are coming to the shore, and just be a huge amount of motion. But it's hard to collect because you need a big giant collector.
There's no free lunch in the universe. When we build a machine.
So the real argument is you can't destroy and you can't create motion in the universe. So there is no idea that you can have this kinetic energy theory where you can just pretend away motion. You can't. It's always got to be somewhere. It's always on the move, and it's always moving something. So motion never stops moving something. It's just that some of the movements are atoms moving.
Machine to extract energy from something, and it rotates something like a wheel or something. It has to come from somewhere, and it's coming in this case from the internal energy inside or in between the molecules in there.
So there's no difference between internal and external, and there's only one concept of energy, and basically the only way you can see energy is in terms of its capacity to move matter. So there's the force, that is the energy, that's the only stuff moving, and the matter is pushed around by it, and we can just watch how much the matter is pushed around, and that'll tell us how much energy the force has.
Thermal motion. So before we close, I want to talk about a couple of different things. Let's talk about air conditioners for just a second. It's a magical device that keeps us cool.
I don't know why he talks like everybody, the audience is an idiot. Oh, it's a magical device. I thought it was a mechanical machine. I didn't think it was a magical.
Cool. In your house, there is a vent that blows nice and cold air on you. In your refrigerator, the inside of the refrigerator gets cold, and so that magically happens somehow. There's no free lunch. It doesn't come from nothing.
Well, then why do you use the word? Why do you even talk about it being magical? It's only magical to ignorant people. The more intelligent you are, the less magical it is.
It comes from the laws of thermodynamics, basically from this process. Here, in a nutshell, in a big picture, is how a refrigerator actually works. What happens is you have some sort of coolant, right? A refrigerant, right? Which is some sort of liquid that can either turn into a vapor or turn into a liquid depending on how much pressure it is under, okay? And what's going on is, what you first do is you take that coolant, it's not so cool at this point, but the coolant, and you compress it with what's called a compressor, and it squeezes it. Now, as you might guess, when you squeeze something, it gets hotter. And
so it's not the heat that you're after. So that's why there's coils on the back of the refrigerator, because you don't want hot compressed stuff. You just want the compression part. And the fact is that, it's not convenient to pressurize it really slowly, because you have a lot of stuff to do. You have a lot of cold to make, and you can't make a lot of cold by compressing it slowly. So you compress it quickly, which makes it hot, and that's a waste. And so then you're stuck having to get rid of that heat. So now when you do expand the gas, instead of going from 500 degrees to 50 degrees, you can go from 50 degrees to 0 degrees.
And so it goes into...
I mean, if you expand a very hot gas, you're going to not get as big a differential. And so your coldest temperature won't be nearly as cold.
To a liquid state, because you're squishing it, but it also gets hotter. And then if you look on the back of your refrigerator, there's a bunch of coils on the back. And the refrigerant circulates through the coils, but it's hot. It's hot and it's under pressure and it's a liquid, right? Because you just compressed it.
Yeah, I just don't know if there's some way they could compress it with like a second compressor, like use one compressor to create the high compression and then compress the gas slower, maybe a higher volume of gas. Well, whatever, I don't need to redesign refrigerators, right? They've probably tried everything and none of it worked.
If you look on the air conditioner of a house, it's the unit that sits outside. There's a lot of grids and coolant loops all over the place. It's called a radiator because it radiates the heat away, and the coolant outside the refrigerator or outside the house then begins to cool off because you just heated it up, remember, through compression. And so you allow it to circulate through these little tubes, and so it gets cool again. It gets cooler. It gets cooler than it was. I'll put it that way. Now here's
right. So you've put it in a vessel. You've put it in a smaller vessel. It's got a bunch of heat. It has to vibrate the surface to get rid of that heat. Okay, and then you can expand it, and it'll go from whatever its relative temperature is to some much cooler temperature because of the expansion. Because now you've increased the surface that it's going to be hitting. The surface has to get a lot colder because you've got a lot more surface that the stuff is going to be hitting. So it just seems like a timing issue. There really should be a shortcut here somewhere.
the thing. It's still at room temperature outside, so you have to make it really cold to make the refrigerator cold. How do you do that? Well, you do that by this. You allow it to go through what's called an expansion valve, and you allow it to expand. The act of expanding the refrigerant and letting it go from a small volume to a larger volume.
There you go, from a small surface area to a large surface area.
Volume makes it cooler, right? And it gets colder, just like this can got colder. If I put this can just like it sits, like if I just make it really, really, really cold, it's cold now. I put it inside the refrigerator, it will help cool my ham sandwich inside of there, right? Because it's cold now, right? But so the same thing happens with...
Right, so when it's cold, that means it's going to take the higher temperature from the outside. That is, it's going to move quicker going in and slower going out, and it's going to equalize again. The pendulums are all going to swing at the same rate again.
The refrigerant, you flash it, you make it change state like that, it gets cold. Then it goes into the refrigerator and it circulates through all of the things in the walls of the refrigerator, or it goes into your house where air blows over the coil.
So yes, it's just coils and they blow air. So yeah. So refrigerators, it's just, there's just a set of coils under one part of the refrigerator, and the rest of you only have a freezer really. It's a freezer, and then they take the frozen air and blow it into the refrigerator.
coils and makes nice cool air which flows throughout your house. Okay? Now, as the refrigerant makes its way through the refrigerator walls, it absorbs the heat of all the food that's in there, warming it up again. So it's not so effective when you have warm coolant in your refrigerator. So then it exits the refrigerator and it goes and gets compressed again, and that heats it up again, and then it goes back outside to do the whole process all over again. So from the top, it comes out of the fridge, gets compressed, gets hot. It cools down through the grids, through the tubes on the outside, the radiator on the outside. And then it goes through an expansion valve, which flashes it, expands it, makes it cold. It goes into the fridge.
Colder.
It takes the heat away from all the stuff inside that's always trying to warm up when you open the door. And then that coolant is not so cool anymore, so it goes back to the compressor, recompress, and so on.
Anyway, so it's not wrong. It's just the idea is... yeah, well, the idea is that what you need is a way of compressing without creating heat.
And you're also using electricity to run the compressor and all the fans and everything else. And so you're always spending more energy than the cooling effect that you're getting on the inside. So it doesn't come from nowhere. Now, the very last thing I'll leave you with is something I learned a long time ago that I think is appropriate for this. I want to teach it to you. It just takes a second. And it's very, it kind of blows your mind a little bit, and it's very helpful as you learn science, especially physics later on. When you think of things under pressure in a can like this, I want you to think of the concept of pressure. Remember we said pressure was force over area. How many newtons per how many square inches or square centimeters?
Right, so then why were you talking about the stupid plunger that was a tiny percentage of the surface area?
That's what pressure is. But a better way or a different way to think about pressure is to think of an energy density. Energy is the potential to do some sort of work. Density is how much energy or how much of whatever you have per cubic meter or whatever. And the best way or a good way to think of pressure...
All right, so the argument would be is that there's two components we know, that increasing the temperature increases the pressure, and electrons and protons all on their own will create pressure. So, you know, both of them have to be thought of in conjunction with each other, in the sense that the very nature of the elastic condition of atoms, that is their compressibility and the fact that they can expand back to some preferable state, and that heat will either make that possible or impossible. But you can't really just say it's just one kind of thermodynamic event, because you really have to account for the fact that at the bottom line this is always about electrons and protons. And that's probably enough. Let me just see here. I don't think
is in units of joules. You learned that in physics class. And distance is in units of meters.
so. This distance formula, this work equals FD stuff is all nothing. It's just completely wrong. And as pointed out, it doesn't work in any real experiment.
And so that takes care of this.
Work is momentum, MV, that's all. It's the only thing that can do any work. Force does work, and it's not about distance, it's about a velocity, frankly, or about a time. Distance is illusionary.
And the area is in units of square meters. So instead of talking about newtons and...
like I said, if a surface is wobbling faster this way and then slow and then fast this way and then slow this way, you can understand that the distance isn't the key. The speed is the key. Alright, so it's probably enough of a video. And so, yeah, an hour. It's, yeah, it's a little more than I thought I'd do. Anyway, I've been reading Newton, and, you know, I haven't gotten around to making the video yet. Just because, yeah, I can see where he didn't have it right. I mean, he really did think it took energy to cause a reflection, and the simple argument is you don't have to use any energy for energy to bounce off of something. There's elastic is a real thing, and things will absorb and throw it right back at you again, and twice the energy doesn't go into the other object. Well, anyway, so till the next time. So I'll probably get to that video next. We'll see if something else happens. But anyway, till the next time, and such and so forth and whatnot. Blah 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 blah.